Welcome to Team 2's presentation for the Wireshark Lab, Course IST 220, Penn State's World Campus. During this lab, you will become more familiar with sniffers, or as they're also called, packet analyzers. You'll also learn more about analyzing Ethernet packets themselves, and finally, you'll learn more about TCP operation and its part in HTTP requests and the three-way handshake. Using the virtual environment from remote locations during this lab may prove difficult. Ask the instructor for instructions to perform the lab on your local PC. Also, don't be discouraged by the Wireshark interface. It does take some time to get used to. Visit the wireshark.org webpage for a tutorial. Here are links to the Wireshark resources and instructions for the Penn State virtual environment. We have provided some more background on the TCP protocol, as it is integral to this lab and will be very important to understand throughout your career in information technology. Pay special attention to how TCP handles packets and guarantees delivery of packets. Okay, you can now start the lab by opening your browser and clearing the web cache. Next, start the Wireshark application. Next, enter the URL shown here into your browser. Now locate and upload the file scarlet.txt. Okay, now you can stop the packet capture. Next, you're going to filter by the TCP protocol. Be sure to type TCP in all lowercase letters and then click the Apply button. So question number 1. What is the IP address and TCP port number used by the client computer source that is transferring the file to 192.168.0.5? Here you're going to select the HTTP message to explore the details of the TCP packet using the Details of the Selected Header window. Select Analyze, then Enable Protocols. Then uncheck the HTTP box and select OK to change Wireshark's Listing of Captured Packets window. If you note the row highlighted in blue, you'll see that IP addresses are found under Source and Destination. Port numbers are found under Packets Details pane in the Transmission Control Protocol. Question number 2. What is the sequence number of the TCP SYN segment that is used to initiate the TCP connection between the client computer and 192.168.0.5? What is it in the segment that identifies the segment as a SYN segment? The concepts here are as follows. The SYN, or synchronized flag, is a TCP packet flag that is used to initiate a TCP connection. It is set for the opening packets of a TCP connection where both ends have to synchronize their TCP buffers. The flag indicates a request to establish a connection. You'll also notice that the application uses relative sequence numbers, so you'll see a sequence value of either 0 or 1. Question number 3. What is the sequence number of the SYN-ACK segment sent by 192.168.0.5 to the client computer in reply to the SYN? What is the value of the ACK acknowledgement field in the SYN-ACK segment? How did 192.168.0.5 determine that value? What is it in the segment that identifies the segment as a SYNACT segment? The ACK flag says that the ACK number is valid. The packet is at least an acknowledgement of data that has been received. If this flag is set to 1, the packet is then an acknowledgement. To find the answer for this question, you can select the packet with SYN ACK in the listing under the Packet List pane. Question number 4. What is the sequence number of the TCP segment containing the HTTP post command? To find this, you'll have to dig into the packet content field at the bottom of the Wireshark window, looking for a segment with a post within its data field. Question number 5. Consider the TCP segment containing the HTTP post as the first segment in the TCP connection. What are the sequence numbers of the first 6 segments in the TCP connection, including the segment containing the HTTP post? At what time was each segment sent? When was the ACK or acknowledgement for each segment received? And what is the estimated RTT value? Wireshark has a feature that allows you to plot the RTT for each of the TCP segments sent. Select any given TCP segment in the listing of captured packets window that is being sent from the client to the 192.168.0.5 server. Then select Statistics, TCP Stream Graph, Round Trip Time Graph. The HTTP post segment is considered as the first segment. The first 6 segments are the ones with the TCP segment of a resembled PDU. In Packet List pane, the acknowledgement segment can be found with the ACK. The sending time and the receive time of the ACKs are tabulated, and the times can be found there. For the estimated RTT value, use the formula estimated RTT equals 0.875 times estimated RTT plus 0.125 times sample RTT. Question number 6. What is the length of each of the first 6 TCP segments? For this, you'll want to click on the packet of TCP segment, expand the transmission control protocol under the packet details pane, and look for the value labeled LEN for length. Question number 7. What is the minimum amount of buffer space advertised at the received address for the entire trace? Does the lack of receiver buffer space ever throttle the sender? In the packet details pane, here you'll expand the transmission control protocol, then expand flag. Look for the field window size. If the receiver window grows steadily until the size that is larger than the minimum, the sender is never throttled. Question number 8. Are there any retransmitted segments in the trace file? What did you check in the trace in order to answer this question? For this question, you'll want to check the sequence numbers of the TCP segments in the trace file. If there's a retransmitted segment, the sequence number of this retransmitted segment should be smaller than those of its neighboring segments. Question number 9. How much data does the receiver typically acknowledge in an ACK? Can you identify cases where the receiver is ACKing every other received segment? What is the throughput, that is bytes transferred per unit time, for the TCP connection? Explain how you calculated this value. Note here that the receiver typically acknowledges 1,460 bytes in an ACK. If the data is doubled, then that segment is ACKing every other. Question number 10. Use the time sequence graph, Stevens, plotting tool to view the sequence number versus time plot of segments being sent from the client to the 192.168.0.5 server. Can you identify where TCP's slow start phase begins and ends, and where congestion avoidance takes over? Comment on ways in which the measured data differs from the idealized behavior of TCP that we've studied in the text. For this, you'll want to select the TCP segment in the Wireshark's listing of captured packets window, then select Menu, Statistics, TCP Stream Graph, then Time Sequence Graph, Stevens. You should see a plot that looks similar to the following. You'll find each dot represents a TCP segment sent. Plotting the sequence number of the segment versus the time at which it was sent. A set of dots stacked above each other represents a series of packets that were sent back to back by the sender. TCP slow start begins at the start of the connection. The identification of the TCP slow start phase and congestion avoidance phase depends on the value of the congestion window size of this TCP sender. If the TCP sender is not sending data aggressively enough to push the congestion state, the value of the congestion window size cannot be obtained directly from the time sequence graph. The idealized behavior of TCP in the text assumes that the TCP senders are aggressive in sending data. In practice, TCP behavior also largely depends on the application. Once you've completed this lab, please remember to log off the virtual machine. Make sure you also read the virtual lab and Wireshark introduction documentation before starting the lab. Another convenient way to save a screenshot is to maximize the Wireshark window and the VMware window on your computer, and then take a screenshot. Thank you very much. That concludes our presentation.